Assalamu alaikum again to the second part of this lecture, the lecture of dimensional analysis and similitude. We went through different parts of dimensional analysis and the two methods that are usually used to develop the formulas, that is Buckingham-Pi theorem and Rayleigh's theorem. Similitude is basically the study of models, how the models are developed, how the models are studied, and how the model analysis is done. In order to know about the performance of any hydraulic structures, whether they are dams, spillways, or the penstocks, before actually constructing or manufacturing them, their models are made and tested to get the required information. You already know what the model is. Model is basically a small scale replica of the actual structure or machine. The actual structure itself is called the prototype, but its smaller scale or even sometimes bigger scale replica is called the model. And we are going to do in this lecture, or this part of lecture, we are going to study the models. Models are very important because we understand that not everything can be done on the actual size of a certain thing. You can't make a dam of the size of the Bela Dam and do different kinds of experiment on that, and then reduce or increase the size and then ultimately make the actual dam. I mean, it's not just physically possible. You have to first make smaller models. You have to go through different kinds of experiments on that model, and then you are going to tweak different things there. Sometimes you would increase one thing, sometimes you would decrease another thing. So models are basically a tool for us to study the effects of different kinds of forces on a particular structure or a particular part of the machine. The model tests are quite economical and convenient, as we said, because the design, construction and operation of a model may be changed several times. And if we have a model, then without increasing much expenditure, we can do all different kinds of experiment on them. So basically what we are going to look into are different kinds of similarity laws, how the models are developed, what kind of similarities we have to look into so that the model can be efficiently developed, and then all the required studies can be easily done on that, so that once a prototype is made, that prototype is a finished product. You just then go for a large scale production of the prototype once everything is done. But before you construct a prototype, your model should be able to give you all the results. So similarity laws help us investigate the natural phenomena in more detail and with ease. So for example, one example can be that you are doing certain experiment in the lab. You are developing a certain pipeline, for example, from one country to another country, and before you actually do the thing, you have to test the thing in the lab. Now actually, in the actual sense, on the ground, maybe that pipeline is for the oil or for the petrol or for any other liquid, but in the lab you are going to do it on the water. You have to develop a pipeline, you have to let the water flow through it. Now we understand that the density of water is very different than the density of oil. Now how to make sure that the experiments that I am doing in the lab are actually the true replica of the prototype that ultimately would be developed? So this is one question, and similarity laws help us investigate these kind of things. And as I said, the advantage is that we can incorporate the details in a model by changing different things to a certain degree, doing the experiments again changing certain things until we are satisfied, and then we are confident that the prototype can now be developed. Of course, the advantage is that you cannot do, as I said earlier, you cannot do all kinds of experiment on the prototype. It's not practically possible to do that. Another thing is that in the labs you have a controlled environment. You can control the temperature, you can control, let's say, the air speed, or you can control the density of certain fluids. So you have more control in the lab instead of doing the things actually in the field. So we develop models and then we ultimately go to the prototype production. As we defined earlier, prototype is a full-size device, equipment or tool with the help of tests on the model. So this is basically the full scale structure. Model is a scaled version of the prototype. It can be smaller than the prototype. In some cases it can be even bigger than the prototype. For example, if you look at the car engine and you look at the flow of the fuel inside the engine and to different parts of the engine, or you look at the oil that is running in different parts of the engine. Now when we are making a model of it, of course we would be making a model which is far bigger than the actual car size. So we might make a model which is bigger than the actual prototype, or we might make a model which is very small than the actual prototype. For example, if you are making a model of a river or of a canal is usually of hundreds of kilometers of length. Obviously you cannot make a bigger model, so you have to make a smaller model of it. So 100 kilometer, you can say that okay, 100 kilometers is represented by 1 feet, and then you have to decrease the size of everything and then develop your model. So model can be smaller, and in certain most of the cases it is bigger than the prototype. Different examples we can always look at our daily life and look at different kinds of examples of the models. Sometimes we have to make the models of ship locks. Ship locks are a kind of structure which is provided besides the dam, so on the left or right hand side of the dam, so that in case your river is used for shipping, then you can have a structure where the ship can pass through the dam structure itself. So models are developed for ship locks. The models are necessary for the sedimentation processes in the river. You are making a dam, or let's say there is a river that is flowing, and you have to make a model so that you can study that how the sedimentation or how the smaller particle would flow in that river or would settle in a particular dam. For groundwater flow simulation, sometimes we need to make a model. We have a bigger container type structure where we put different kinds of soils in it, clay soils and silty soils and different gravels, and then we let the water go through that different structure and we study the behavior of water. So groundwater flow simulations are done there. Air and water turbines, spillways of dams, these are different examples of the models, or let's say the similitude study, for which we consider developing different kinds of models. Now, two ratios that we need to consider in model development are the scale ratio and the model ratio. You would come across in few slides, you will come across different numericals where we would be given the scale ratio and we would be asked to develop a certain kind of model. So if we know the scale ratio, we would be knowing how much smaller or how much bigger we are going to make a model. So scale ratio would be needed there. Model ratio is just the reciprocal of the scale ratio. Mostly we would be using the scale ratio in our studies, but sometimes model ratios would also be considered. So basically scale ratio is equal to any value of prototype divided by any value of the model. So for example, if we are looking at the length, the scale ratio of length, L is here denoting the length, then the length of prototype divided by the length of model would be our scale ratio of length. The vice versa, of course, is then the model ratio. Sometimes we would be looking at the velocity ratios, and we would be saying that the velocity is decreased to, let's say, 10 times the velocity in the prototype. Then our scale ratio would obviously be 10, because 10 is the velocity in the prototype, 1 is the velocity in the model. So then in that case it would be Vp divided by Vm, 10 divided by 1, and that would be equal to Vr, that is the scale ratio of the velocity. So we would be sometimes using the scale ratio, sometimes we would be using the model ratio. You have to remember that the scale ratio is always any quantity of prototype divided by any quantity of the model, the length, velocity, acceleration, anything. So these are basically the two ratios that we are going to use. Important thing is the similarity between the model and the prototype. You see, we have to make sure that the model that we are making in the lab truly represents the prototype. If there are differences in both the things, then once we go to the prototype or we go to the field, then everything would be wrong. We have to make 100% sure that the model that we are developing is exactly the same as the prototype, except of course the size of it. You are making the thing smaller, but the rest of the things are the same. You have to ensure that the velocity is the representative of the velocity in the prototype. It can be smaller or greater, but it should be representative. And we'll see how we make sure that these things are done. These things are done by ensuring different kinds of similarities. The first similarity is the geometric similarity. It is a desirable feature that has to be present in the model. The geometric similarity basically means that both the model and prototype should be identical in shape. They can be different in size, but their shape should be identical. If we are making models for flow, then the flow patterns should be identical, which basically means that if in prototype the flow is laminar, then in the model also the flow should be laminar flow. It wouldn't make much sense if the flow in the prototype is laminar and the thing that we are making in the lab, the model, has a flow which is turbulent. Of course the results would not be then appropriate results. So we have to make sure that the flow patterns are the same. The problem is that it is not always easy to ensure the geometric similarity. And why it is not easy to ensure this thing? Because you see, for example, let's say you are making a model of a very big pipeline. Again, the example of a pipeline which is transporting oil from one country to another country. Now, if you decide to make the model very small, then in the model there would be certain forces occurring because of the very small size of pipes, which in reality in the prototype are not present. You see the surface tension, for example, or the surface roughness of pipes. If you reduce your pipes too much, there would be unnecessary forces that we would be generating which are not present in the prototype. So it's not always easy to just say that okay, reduce the size 10 times or 100 times. You have to look whether because of this reduction in size, because of the decision that I am making the size smaller, you have to make sure that you are not increasing something else, or you are introducing certain things which are not present in the actual sense. That is important. Then sediment transport problem. For example, you are studying the effects of sediments in the Tarbela Dam. When you are making a model, you have to ensure that the particles that are introduced in the model are actually representative of the particles which are actually flowing in the Kabul River or in the Indus River. You see, so these are the problems that we have to consider. Then another problem is difference in horizontal and vertical scale. Let's say you are making a model of a river which is 200 kilometers long. If you now decrease your river to, let's say, from 200 kilometers, you are reducing the size to 2 feet or to 2 meters. Even from 200 kilometers you are reducing the size to 2 meters. Then what are we going to do with the depth? This is another problem, because if you, with the same ratio, if you are now decreasing the depth of water, again you are introducing capillary effects, you are creating other problems for it. So these are the problems that have to be looked into when we are providing the geometric similarity. Another thing that we have to ensure is the kinematic similarity. Kinematic similarity is basically the similarity of motion. It basically is that there should be a geometric similarity, and then there should also be the similarity of motion, which basically is the ratio of velocity at all corresponding points in the flow of model and of prototype. If at the corresponding points in the model and in the prototype the velocity or acceleration ratios are same, and velocity or acceleration vectors point in the same direction, then we can say that the two flows are kinematically similar, because first of all the velocities are the same, and then the acceleration vectors, that is, if the water is accelerating or deaccelerating in the prototype, then these effects are same in the models. As we said, for the geometric similarity, we have the length ratio equal to length of prototype divided by length of the model. Similarly, if we are looking at the velocity ratio, which is a kinematic property, then the velocity ratio should be equal to the velocity in prototype divided by velocity in the model. Similarly, if this is the velocity ratios, then the time ratio and acceleration ratio can also be calculated in the same way. Length divided by velocity is basically the time. Length is meters, velocity is meter per second. When we divide meter by meter per second, we would be left with the second. Second is then the time ratio. So time ratio would be equal to the length ratio divided by the velocity ratio. Length ratio you already looked into. Length ratio is the length of prototype divided by length of model. Velocity ratio is given here, velocity of prototype divided by velocity of model. So basically my TR, or the time ratio, is equal to the length ratio divided by the velocity ratio. In the same way, if I'm looking at the acceleration ratio is LP divided by, or LR divided by the T square R. Length ratio is given in the earlier slide. Time ratio is given here, and ultimately for the acceleration ratio we'll come across this formula, which is equal to the velocity ratio squared divided by the length ratio. So these are the kinematic similarity conditions that we have to observe. You just take pen and pencil, or pen and page, and just calculate these things, and then you would be understanding these things. So first of all, just write this length ratio this length ratio is equal to length of prototype divided by length of model, then write the velocity ratio, and then do all these things, and you will come across these equations. This is just simple manipulation of values. Third kind of similarity is dynamic similarity. Dynamic similarity is the combination of geometric similarity plus the kinematic similarity that you looked into earlier. Additional thing is the ratio of forces should be the same in dynamic similarity. Yeah, so this is the third kind of similarity that we have to ensure. The flows in the model and in the prototype are dynamically similar if at all the corresponding points identical types of forces are parallel and bear the same ratio. So we have to ensure that the forces that are in the prototype and in the model are the same. And what are the forces that usually we have to consider? These are also given here: the gravity forces, the pressure forces, viscosity forces, elasticity, surface tension, and inertia forces. These are all forces that you are aware of. So basically, if we are looking at the inertial forces at a point in a model, then we have to ensure that the inertial forces in the model and in the prototype are the same. So the force ratio should be the same, just like as we looked at the few equation earlier. And obviously, if the system is in dynamic equilibrium, then all these resultant forces should be equal to zero, whether they are gravitational, pressure, or elasticity forces, or inertial forces. Okay, another very important thing are the dimensionless numbers. You have used different kinds of dimensionless numbers till now. You have used Reynolds numbers, you have used the Froude number, and we have defined earlier all these numbers. But there are, in addition to these Reynolds and Froude number, there are other ratios or dimensionless numbers that you should be aware of. Why we are looking at these dimensionless numbers is that sometimes we have to ensure that the Reynolds number in the model and in the prototype is the same. And then you have to look at the ratios. So that's why it is important to understand what the Reynolds number is and what are other different dimensionless numbers. First of all, Reynolds number. We already know that Reynolds number is the ratio of inertial forces to the viscous forces. Fine. And the examples where the Reynolds number would be used are the movement of airplane in the air, the movement of submarine in the water. And we have to ensure that the inertial forces, which basically is given by this equation, the length square, velocity square, and density, and then the viscous forces, the same thing with the dynamic viscosity here, and ultimately we reach up to this equation, to LV by absolute viscosity. So this is basically our Reynolds number. So the ratio of Reynolds number in the model and in the prototype has to be looked into, and we already said that Reynolds number would be important where motion of, for example, if we are considering the motion of submarine which is completely underwater, then we have to consider the Reynolds number there. If we have to study the velocity of air around the automobiles and aeroplanes, then we have to consider the Reynolds number. So these are different practical areas where Reynolds number would be important for us, and we will be ensuring that the ratios of this dimensionless number is the same in the prototype and in the model. This is just an example of the same thing. If there are two pipelines flowing with different fluids, and we have to ensure that they are dynamically similar, then we just have to ensure that the Reynolds number ratios are the same. So let's say this is the Reynolds number in the model, this is the Reynolds number in the prototype, and we have to ensure that this ratio is same at all places in the model and in the prototype. Another dimensionless number that you have used quite a lot is the Froude number. You see, when we were calculating the critical flow and supercritical flow and subcritical flow, for us the criteria was Froude number. And what basically is the Froude number? Froude number is just the ratio of inertial forces and gravity forces. We use it in the areas where we have to look at for example, the wave action on the ships. This is area where we have to consider the Froude number. Froude numbers is used in the flow over notches, flow over weirs, flow over the spillway of the dam. These are different areas where you have to look at the Froude number, and you have to ensure that the forces, this particular force ratio of Froude number is the same in the model and in the prototype. Mach number is another dimensionless number. You might have heard the name Mach number, which basically is associated with the speed of sound. You see, when we say that F-16 can fly with the speed of Mach 2, we basically are saying that F-16 can fly 2 times the velocity of sound. So it's a ratio of inertial forces to elastic forces. It's just velocity of a certain body divided by the sonic velocity. Sonic velocity is the velocity of sound. And anything can be used, whether velocity of a body in the air, for example, or the velocity of air against a certain body. So both of them can be used, and usually we use the Mach number in the flow problems at very high velocities, for example, high velocity flow in pipes, or motion of high speed projectiles and missiles and torpedoes and those kind of things. Weber number is basically the square root of the ratio of inertial force to the surface tension force. So the thing is under the square root. In the numerator we have inertial forces, in denominator we have the surface tension forces, and this Weber number is also a dimensionless number, which is usually used in the flow in groundwater when the flow is very slow, and when the surface tension are the important forces to be considered. Also, the flow of blood in veins and arteries is usually modeled through the Weber number. So this is another dimensionless number. Euler number is another dimensionless number, which is basically an inertial, with the ratio of inertial forces to the pressure forces. This is basically used in the conditions where you have to stop the flow of water. For example, let's say water is flowing in the penstock with a very high velocity and you have to stop it immediately. Then in those conditions the Euler number has to be considered, because you see it's a inertial force, which is basically the velocity of water inside a penstock, and when we stop it, then obviously the pressure generation is the issue. So these two numbers are then considered in those kind of problems. So these were different kinds of dimensionless numbers that are considered in the fluid mechanics. Now let us look at different problems. Now, how are we going to develop the formulas here? These are the formulas that you have to remember, not the whole derivation of it, but at least the final value should be remembered. Another thing that you have to keep in mind is that in this chapter capital value or capital letter would be representing the value in the prototype, and the smaller value would be representing the value in the model. So for example, small h is the head of water over the model. Capital H would be the value, the same value, that is head of water or the prototype. Velocity would be the velocity of water. If it is small v, then the small v would be representing velocity of water or any fluid in the prototype, in the model, and capital V would be showing the same velocity in the prototype. Fine. Capital would always be the values of prototype. Smaller values or smaller digits or alphabets would be the same thing in the models. So for example, if I am looking at this formula, this is small v is equal to coefficient of velocity under root 2gh. So this is velocity in the model, g in the model, small h or head in the water. If it is capital V is equal to CV2GH, then this velocity is the velocity of prototype and H is the head in the prototype. If we are now getting the ratio between these two velocities, we have to look at the velocity in the model divided by velocity in the prototype. If we divide these two over each other, coefficients are constant, we can get rid of them. 2 is constant, g is constant. Ultimately you have just under root h divided by under root capital H, and ultimately we get the lambda, which is 1 over LR. And then we already have looked at this lambda in the previous slide, which was the reciprocal of the scale ratio. You see where here we are using velocity in model divided by velocity in prototype. Now model by prototype was the model ratio, and we said that model ratio is the reciprocal of the scale ratio, and scale ratio was shown as LR. So 1 divided by LR is this thing, and then when we now just rearrange the things, then we can find out that the velocity in the prototype is equal to the velocity in the model, and then in the under root we have the length ratio, and length ratio is the length of prototype divided by the length of the model. Fine. So this is these are different equations that we are going to use. You can do the derivation yourself, quite easy, but you have to remember finally this formula for the exams. Similarly for discharge, in the books this formula is proved. I'll also show you here in a couple of slides how this formula is shown, that the discharge in the prototype is equal to the discharge in the model multiplied by the length ratio raised to power 5 by 2. Again, do remember that in this chapter capital values are representing the prototype values, smaller alphabets are showing the model values. Do not confuse this smaller q with the specific discharge that we did in the open channel flow. Fine. This has to be remembered. Sorry. So now these are the numericals. This one we already did in the previous slide. Basically, if H is the head of water over the model, capital H is the head of the water in the prototype, and then we can simply, as we said earlier, we can find out this formula. Then a very simple example here, you see the velocity at a point on a spillway model of a dam is 1.3 meters per second for a prototype of model ratio 1 to 10. Now you have been given the scale ratio, which is 10. What is the velocity in the prototype? Now this is a question. So you have been given the velocity in the model, which is 1.3 meters per second, and then you have been given that the scale ratio is equal to 10. So what would be the velocity in the prototype? We just use this formula, that velocity in the prototype is equal to the velocity into the model multiplied by the scale ratio under the root. Scale ratio is given us as 10, so the answer is 4.11 meters per second. So if in the model the velocity is 1.3 meters per second, then in the prototype the velocity would be 4.11 meters per second, given that the scale ratio is 1 to 10. Very simple. It's easier than the numericals of physics that you have done maybe in class 7 or class 8, so there shouldn't be any problem here. This is the proof that I was telling you about. The discharge, the derivation of the discharge formula, that is discharge in the model, in the prototype is equal to discharge in the model multiplied by the scale ratio raised to power 5 by 2. Now, very easily derived. Small q is equal to small AV, capital Q is equal to capital AV. We find out the ratio of the two. Fine. Now this ratios, we are using here 1 by s square because we already know that this is now the model ratio. We have to convert it to the scale ratio, and because area is meter square or square meter, so we have to use 1 over s square. Similarly, this ratio was earlier proved to be 1 divided by under root s. We just put all the values, and finally we come across q is equal to q s 5 by 2. And this is the formula that you have to remember. This is the simple derivation of it. You can go through it in your books, but very easy. But ultimately you have to keep in mind this formula, that the discharge in the prototype is equal to the discharge in the model multiplied by the scale ratio, whatever the scale ratio is given to you, raised to power 5 by 2. For example, a very simple example here, the discharge over a model which is reduced to 1 to 100 in all its dimension is 1.5 liters per second. So basically you have been given the scale ratio, which is 100, and you have been given the discharge in the model, which is 1.5 liters per second. Now the question is, what should be the corresponding discharge in the prototype? Just use the previous formula, put all the values, you'll get the thing. Now these are the comparatively easier numericals. There would be numericals which would be a little bit complicated. For example, this one, you go through it yourself. It's quite easy. It is a solved example, so just go through it, you would be able to understand it, I'm pretty sure. If there are any questions related to these things, then do put the questions on NMS. I'll try to answer it as quickly as possible. I'll be uploading the assignments for hydraulic engineering lecture of this week on the LMS. It would be, as I said earlier in the first part, it would be due to be handed in by Friday, and it's very necessary that you hand it in through LMS so that your attendance is generated automatically. Again, if there are any questions, please use your LMS. Wish you best of luck. Assalamu alaikum.